Yeah, you said the lungs don't seem to want to train. So maybe
Well,
elaborate
it's
on that
a
a little bit.
curious thing, isn't it? This is curious. Um, so my personal history with this was that I told you were asking me a bit ago how I got interested in the respiratory system, and I was telling you about how perfect it was back in the first started to look at this, and I still believe that to a great extent. And for example, if you just look at the oxygen exchange by the lung,
Mm-hmm.
and you measure arterial blood in people who aren't highly trained, and you see that the arterial PO2 is controlled exactly at resting values. It never falls.
Mm.
You can exercise till you're falling off the device, and it's maintained. And you never see the CO2 rise. In heavy exercise, it's controlled perfectly at resting levels. During moderate exercise and heavy exercise, it falls. You get a hyperventilatory response. All good. In the early 1980s, and I can't even remember why now, we started to look at people who were really highly trained. So I think the first studies were done in the late 70s that we tried. And we had 2 Olympian 1,500-meter runners that were training for the Moscow Olympics, which unfortunately the Americans never ended up going. They boycotted. But these guys were trained. And 2 of them were local. They were around Madison, Wisconsin. And so for this study, which is like I said, I don't remember why, we had them come in, put an arterial catheter in, ran them on the treadmill. And both of them were doing fine. And then they got into about 3/4 to their max and up to max. The arterial PO2 fell during exercise. I'd never seen this. Now, when I look carefully in the literature, you can see the odd example, okay, of one. Scandinavian literature had it. There was some study out of Minneapolis by Rowell that showed it, but he hadn't actually measured blood gas saturation. I thought, wait a minute here. Does this mean that the highly trained person will kind of outrun the lungs' ability to exchange gas? And we knew from studies done earlier in our lab, anyway, that we measured diffuse capacity of the lung in several different groups of athletes over a training session. And their VO2 max went up with their several weeks and months of training. These were intercollegiate athletes. But nothing happened to the diffuse capacity of the lung. And if you look throughout the literature, there wasn't a lot on it, but you could see athletes don't, you see the odd one with a higher diffusion capability in the lung, but it's not consistent. Well, if you have a higher demand for oxygen transport, but a major organ that delivers oxygen has not adapted, will it get to the point of failing as a gas exchanger? Well, we went ahead and studied, I think, 20 of these athletes at the time, and a little more than half of them showed this hypoxemia. And so that's a long time ago, and that's now been confirmed. And we still don't know why some of them do and some of them don't. I wish I could explain that. If we had better methods of imaging the lung during exercise, the small airways in the alveoli, we could probably tell what's going on. But it's a matter of them not being able to distribute ventilation and perfusion perfectly in the lung during exercise. And when you have your muscles extracting so much oxygen and it comes back on the venous side almost completely desaturated, you better have a near perfect gas exchange system, and we don't. And it's the fact that the cardiovascular system and the locomotor muscles and the red cell mass has beautiful adaptations to training, gorgeous, but the lung doesn't seem to want to train. Okay, it's not that the lung isn't adaptable. If you look at people born and raised in high altitude, the lung grows in hypoxia, at least in maturing animals and people. We studied the natives of Leadville, Colorado, 3,100 meters. They'd only been there 3.5 generations when we studied them. Paltry compared to Swiss or people living in Tibet or Ethiopians or Peruvians. Tibetans have been there 30,000 years. Peruvians, 10,000 years. So this was peanuts, but their lungs were unbelievable.
Can you give an idea
in
of the increase in, could you give an idea of the increase in the lung, I guess, volume or lung size?
No, not volume so much. I know that's in the literature, volume. It wasn't volume so much. It was diffusion surface.
Oh, okay.
And when that's studied in animals, where you can look at the more detailed morphology of lung, it's the number of alveoli and the number of capillaries. Now, we have 300 million of them ourselves, but this has even more. 20 to 40% increase in diffusion capacity of the lung at rest and exercise. And they exchange oxygen from alveolus to blood so much more efficient than we do. And they hyperventilate much less during exercise. So pretty ideal adaptation if you're living in a hypoxic environment.
Right. Is that something that can be changed within a lifetime, or is that a generational thing where you essentially have to be born with the genetics of your ancestors having, I guess, evolved at higher altitudes for, you know, a certain amount of time to benefit from those, I guess, genetic predispositions? You
do not. If you move there during maturation, the lung matures up into adolescence. It's got a long growth period. Unfortunately, it starts to decline in our late 20s. Isn't that terrible? So what a terrible thing to do to humans. Anyway, so yeah, you can see this. You can take a young animal from sea level and shortly after birth move them into a hypoxic environment. You'll see this, just like we saw in the humans of Leadville, that those that were born at sea level moved with their parents to high altitudes as children show this very similar adaptation and diffusion capacity. So the lung will adapt. If you do what's called a pneumonectomy, take out part of the lung and look at adjacent areas of the lung, you'll see growth, substantial growth in fairly short period of time. We know in small animals, if you change their nutrition, starve them, the lung will be affected by that. So it's not that the lung is not adaptable, but to the exercise or so-called training stimulus, it doesn't seem to be. Now, I'm seeing some stuff more recently on, just saw an article out of Poland in mice, training mice and seeing the volume mitochondria in the lung, not the muscles, in the lung actually increasing. I thought that was really interesting. I don't know what it means to function. I have no idea yet, but I thought that was interesting. I see another one in which rodents were made to smoke cigarettes, and then they saw deterioration in diffusion surface of the lung and in lung function. If they trained those rodents but kept them smoking, we do crazy experiments. You can see that this deterioration in the lung diffusion was actually constrained a bit by the training.
Okay.
Well, I know those are a little far out kind of things, but it's an idea that there might be something and we know now, beautiful work from Denmark over the years, that contracting muscle is an endocrine organ and it produces cytokines. We always thought those, like IL-6, for example. We always thought those cytokines were harmful. Well, maybe to some extent, but there are also a lot of benefits of these cytokines. And now that's being explored in treating cancer with exercise. Look at all these ideas. And it could be that might also, the training the locomotor muscles might also have an effect on inflammatory responses to the lung. I still haven't seen any really good evidence, but that has to be investigated in health and disease. So really needs.
So sorry to cut you off. So from what you said just before, there is a pulmonary diffusion limitation that does exist, and the only way to combat that is to move at high altitude when you're a child and then grow up there. Would that be kind of a way to put it?
Yeah. And some people have wondered why. You remember who did so well in the Mexico City Olympics at 7,500 feet?
I don't.
Kenyans.
Oh, right.
It's the first time, you're too young. It's the first time we heard of the Kenyans.
Yeah.
And what I remember the best is that the Kip Keino from Kenya beat by at least 20 yards the American record holder, world record holder in the 1500 meters. And that was Roman. And the marathon was won, I think, by, I can't remember, it was from a high altitude country. And I just wondered, now, does it help you as an athlete compete at sea level? Well, maybe. But it certainly helps you if you're competing at high altitude, for sure.
Right.
Can't say for sure, but I would say yes. If I don't know of any other way to increase the diffusion surface other than to expose people to epoxy. Now, that's going to come with a price because oh, this is really good.